What's up, Simians? Back again. Let's wrap this bad boy up, okay? We're almost there. I got some water. I rested a little bit. Now it's time to keep on trucking, okay? Number 6. Calculate the number of moles of magnesium oxide. Calculate the number of moles of magnesium oxide that, come on now, that will be produced if 13 moles of oxygen starts the reaction. Okay, so again, we have to balance this reaction. First step out the gate. Okay, so we have magnesium, oxygen, magnesium, oxygen. Here we have 1, here we have 2, here we have 1, here we have 1. Okay, so I'm going to need a 2 out here. It's going to change these both to 2, so I'm going to need to put 2 here. Okay, now it's balanced. All right, now we need, so let's look at our known. First of all, we need a number, 13 moles of oxygen. So we know that 13 moles of oxygen is going to start this reaction. 13 moles of oxygen. Okay, now our unknown, what we're trying to find out, what we're trying to calculate is the moles of magnesium. Moles of magnesium oxide that are going to be produced if you have that many moles of oxygen. Okay, so our conversion factor here, again, is going to be our ratio. So we're trying to go from moles of oxygen to moles of magnesium oxide. Okay, so there's an imaginary 1 here, so we're just looking at our ratio. Which is our ratio of moles of oxygen to moles of magnesium oxide in this reaction. So that ratio is 1 mole of O2 for every 2 moles of magnesium oxide. Okay, again, I got that from the ratio in the equation of the ratio of moles of oxygen to moles of magnesium oxide. Okay, so let's set up this equation. So we start out with our known. Our known is that we have 13 moles of oxygen. We need to multiply that by our conversion factor. Okay, and we know that we want to cancel moles of oxygen because it's what we're starting with, so we need to put it in the denominator, drop it like it's hot. Okay, we need to cancel this. So when we look at our conversion factor, we have to flip it from how we originally wrote it. Okay, so 1 mole of oxygen is going in the denominator, and 2 moles of magnesium oxide will go in the numerator, so that is what we end up with. And then the math is just going to be to multiply 13 times 2 divided by 1. So divided by 1 is irrelevant. We know we're canceling these. So we're just going to be left with 13 times 2, which is going to be 26 moles of magnesium oxide. Okay, because that is what we are left with. Okay, so again, just get the ratio, multiply it out. All right. Number of moles in this many grams of sodium hydroxide. So let's get right into it. Our known is going to be the number we're given, 20.67 grams of sodium hydrox. Okay, sodium hydroxide, NaOH. Forgot to switch colors. So grams of NaOH is what we're given. What a nice color, how pleasant. And our unknown, what we're trying to find, okay, our calculate number of moles. So we're trying to find moles of sodium hydroxide. Moles, NaOH. Okay, so then our conversion factor has to allow us to go between these two things, which means we're going to have to find the molar mass. Whenever you're going from grams to moles, moles to grams, you get the molar mass because we get molar masses in grams per mole. So we have NaOH, means we have sodium, oxygen, hydrogen. Sodium, we have each one once, so I'm not even going to put the numbers. 22.99. When I say numbers, I mean the multiples. It would just be one for each one. For oxygen, I'll do 15.99. You could do 16. You'll get the same thing. Okay, add these all up, and I'm going to get 39.99 grams per mole. And every time we see that grams per mole, we are happy because that's an automatic conversion factor. So I'll set up that conversion factor here. We have for every 1 mole of NaOH, we have 39.99 grams of NaOH. Okay, so every 6.02 times 10 to the 23rd molecules of NaOH weighs 39.99 grams, 40 grams basically. Okay, so now we set this up. We take our known, which is 20.67 grams of NaOH. We need to multiply that by a conversion factor. Multiply by our conversion factor, which we need to set up so that grams cancels. We want our known to cancel, so we need to put grams of NaOH down here. Okay, and that is how it's already set up, 39.99 grams of NaOH for every 1 mole of NaOH. So this turns into 20.67, just do this real quick to help anybody with OCD. Okay, so we're canceling our grams of NaOH here, and we're going to be multiplying 20.67 times 1 divided by 39.99. So 20.67 divided by 39.99. We have 4 significant figures in both of these, so we're going to be able to keep 4 significant figures. And some of you were rounding and you were just turning this into 40 grams. If you're going to round this, round it to the hundredth. So even if you're going to round it to 40, which I'm okay with, it needs to be 40.00. So you keep those 4 significant figures. Okay, so we're keeping 4 significant figures. It's going to be 0.5169 moles. Is that the wrong one? That's right. Moles of NaOH. Okay, so that's how you do that one. Again, grams to moles, we always got to get molar mass. Okay, another volume one. So our known number that we're given, 0.8 moles of chlorine gas. Moles of Cl2. Our unknown, what we're going to be trying to find, let's see, what is volume? So we're trying to find volume of chlorine gas. Volume of Cl2. So we need a conversion factor that allows us to go between volume and moles, and that is another, just like Avogadro's number, is a constant conversion factor. We know that for every 1 mole of Cl2, we have 22.4 liters of Cl2. Okay, every 1 mole per 22.4 liters of gases at standard temperature and pressure. So our known, 0.8 moles of Cl2, multiplying that by conversion factor. Okay, and we need to drop moles of Cl2 like it's hot to get rid of it. Okay, so it's 1 mole Cl2 for every 22.4 liters of Cl2. So my moles are going to cancel, and I'm going to do 0.8 times 22.4. And now this is one that a lot of you messed up with significant figures, because your answer you're going to get is 18 something, and a lot of you rounded to 18. But you see here you only have 1 significant figure. 18 has 2 significant figures, so you have to round this very broadly. You have to round it to 20 liters of Cl2. and that is your answer. Okay? Now, bonus. The bonus ones, I don't think this was really any harder than the other ones, but I think just the fact it was bonus kind of scared you guys, because a lot of you got this wrong when I didn't expect you to get it wrong. So our known is that we have 9.06 liters of calcium carbonate. 9.06 liters of calcium carbonate. Sorry, I should have adjusted my color here. Okay, so liters of calcium carbonate are unknown. Okay, we're trying to find how many grams of calcium carbonate. I'm going to change my color. Okay, so our conversion factor, well, our conversion factor is given to us here. Okay, some of you might have been confused, but whenever we're going from grams to liters, there is no constant for that. That's a density. Grams to liters, going between grams per liter is a density. So you have to be given a density. The only density you might have to know is water. But for anything like this, you're going to be given the density, which we are right here. So we're given that it is 2.71 grams of calcium carbonate per, I should have done this, which color, 2.71 grams for every one, color was that? For every 1 liter of calcium carbonate. Okay, so that density is our conversion factor. Just like molar mass is a conversion factor, that tells you grams per liter. This is how you break it down to grams per liter for calcium carbonate. So we take our known 9.06 liters of calcium carbonate. We're trying to cancel liters and get this all into grams. So we set up our conversion factor, and we're going to drop liters to the denominator so it will cancel. So 1 liter for every 2.71 grams of calcium carbonate. This will allow us to cancel liters, end up in grams. So we're going to get 9.06 times 2.71 divided by 1. So just multiply. We have 3 significant figures in both these, so we're going to keep 3, and we're going to get 24.6 grams of calcium carbonate. Okay, so this is your answer here, 24.6 grams. We'll use a density to go between those. Okay, now this one took a little bit of extra thinking, but I think that's dope. So, our known. So we have these percentages up here, which might throw you off a little bit, but still are known. How many grams of table salt would contain 2.4 grams of sodium. So our known is 2.4 which color? 2.4 grams of sodium. Okay. Our unknown is grams of sodium chloride, table salt. Now our conversion factor. This is tough. I understand that this is tough. So we're trying to figure out, we need some way to relate grams of sodium chloride to grams of just sodium. Now up here in the first sentence, we're told that sodium chloride contains 39.37% sodium by weight. Okay, so if you just break it down into the weights, you have 39.34% sodium. So what's a percentage out of? Percentage is out of 100. So that tells me that for every 100 grams of sodium, for every 100 grams of sodium chloride, I have 39.34 grams of sodium and 60.66 grams of chlorine. So I can set that up as a conversion factor because it's an equivalency, it's a something per something else. So I have, well, for every 100 grams of sodium chloride, okay, for every 100 grams of sodium chloride, I could do this with any number if I do the math to figure it out, but obviously with a percentage, it's easiest to do 100% or 100 grams. For every 100 grams, I have 39.34 grams of sodium, okay? Now, once I have these three things, my known, my unknown, and my conversion factor, especially for these one-step conversions, your work is pretty much done. It's just plug and chug at this point. So my known 2.4, and even though, so what I'm trying to say there is that even though this was kind of harder to figure out our stuff, once we have it, we're good. It's no different than any other one once we have this. So I put my known, I multiply it, I'm gonna multiply it by a conversion factor. I want grams of sodium to cancel, so I'm gonna put this down here, and I look at my conversion factor, I see that it's 39.34 for every 100 grams of sodium chloride. So that means that my grams of sodium are going to cancel. Then I get, so this is a little bit different in that normally what we were dealing with above in the above problems, we had a 1 in one of these places. This isn't so. It's going to be 2.4 times 100 divided by 39.34. But that's not that bad. So you just do that in a calculator, 2.4 times 100, 240 divided by 39.34. Significant figures, we only have 2 out here, so we're only going to be keeping 2. So it's going to be 6.1, and we're going to end up in grams of sodium chloride. So what this just told us is that in every 6.1 grams of sodium chloride, there are 2.4 grams of NaCl. And you could probably do this differently mathematically, but this is how you do it with conversion factors. So thank you guys for watching. I appreciate the hard work, checking your answers, making sure everything's right. Yeah, that was a lot of talking and a lot of math, but I'm gonna go take a